All right, welcome to another edition of Uncle Kemi's online class. Today, I will be taking you on a very important topic under gas law, which is titled Graham's Law. So join me on the next edition where we'll be dealing more on the calculations and the explanation involving Graham's Law. Now, let's take, for instance, you have two individuals. One is very fat and while the other one is very slim. Or in other words, one is light in weight while the other one is very heavy in weight. And if you set these two individuals on a race, which one will you think will get to the end point at a short time? The answer is simple. The one that is light tends to move faster than the one that is heavy. Why? Because the one with a very heavy mass tends to move slower compared to the one with a light mass. So that's just how it is for different gases. As we all know, we have so many gases. We have oxygen, hydrogen, neon, and so on. We can name them. And it's important for you to also know that these gases that I mentioned, they have different molecular weights. In other words, it means their weight varies. They don't have the same weight. Now, let's take, for instance, for oxygen, which is known to have a molecular mass of 32 grams. Why that of hydrogen just has a mass of 2 grams? These two gases, oxygen and hydrogen, their masses varies. But when you look at the mass, the variation of their masses, you will observe that the mass of oxygen is heavier and bigger and larger than that of hydrogen. Now, when you release oxygen and hydrogen at the same time to diffuse through a particular environment or a particular medium, you will observe that hydrogen tends to move faster than that of oxygen. Why? Because hydrogen has a very light weight compared to that of oxygen. It is just the way we compare it to human beings. The human being with a very large mass and a human being with a very light mass. When you set the both of them on a race, the one with a light mass tends to move faster than the one with a large mass. Now, that is just what Graham's law is explained. In the case of Graham's law, we are going to be dealing with different gases, two gases, which will be released at the same time or will be released. And we can use Graham's law to determine the molecular mass of the gas or to know the time it takes for the gas to get to a particular point. That is what Graham's law is explaining. In other words, Graham's law will compare the rate of diffusion between two gases set to move in a particular medium. Now, in other words, what is Graham's law saying about? Graham's law states that the rate of diffusion of a gas is inversely proportional to the square root of their density. In other words, the rate of diffusion of a gas is inversely proportional to the square root of their molecular mass. Now, let's go into the solving parts of Graham's law. Now, you can look at what we have on the board. This represents the formula or equation that we can use to solve for Graham's law. You can see my R1 and my O all over R2. What is the meaning of the R1? The R1 represents rate of diffusion of gas 1. What is the meaning of R2? It represents rate of diffusion of gas 2. In this case, let's take, for instance, we are dealing with two gases. The first gas is oxygen, while the second gas is hydrogen. In this case, the rate of diffusion of gas 1, this is gas 1, this is where we insert it, and gas 2, this is where we insert it. Now, let's not forget, if rate represents the rate of diffusion of the gases, what is the formula for solving for rate? Rate also means the volume of gas all over time. What am I saying? When the volume of gas is given to you in a question and the time it takes to diffuse through a particular medium is also given, you can use those parameters or variables to determine the rate of diffusion of that gas. Let's take, for instance, the rate of diffusion of oxygen. Let's take, for instance, if we have a volume of 20 cm3 of oxygen gas and it was able to move through a porous spot in 2 seconds. Let's say the time taken is 2 seconds. Now, how do we calculate the rate of diffusion of the gas? Now we'll go rate of diffusion, which is the volume of the gas all over time. Now, the volume of the gas here is 20, that is for here, while the time it takes to diffuse through that porous spot is 2 seconds. So what will be my rate of diffusion of gas oxygen? It's now going to be what? 10 cm3 per second. So that is how to solve for 10 cent cube per what? Seconds. This is it. Now, in this case, now let's go to the part that is a little bit complex according to how students will always say. My rate 1 is the rate of diffusion of the first gas. In this case, I'm dealing with oxygen. So my rate 1 will be the rate of diffusion of oxygen. My rate 2 is the rate of diffusion of hydrogen. What about my molecular? The M2, it represents the molecular mass of the gas 2. So this simply means your M2 will not be oxygen. Your M2 will be gas hydrogen, because the second gas here is hydrogen. So that's what we are going to insert here. So be careful, your R1 over R2, don't ever try to put M1 over M2, because they are inversely proportional to each other. So they cannot be directly proportional to each other. So when we say R1 over R2 is inversely proportional relating with the two gases, in this case, my M2 is hydrogen and my M1 is oxygen. And also we have our density 2. What is the meaning of my density 2? Is the density of the gas hydrogen, and D1 is the density of the gas oxygen. And here is my time, the time taken for the gas 2 to diffuse, time 1 is the time taken for the gas 1 to diffuse. If you are able to understand this formula or this equation, you will be able to solve questions related to gas law. Let me take it one more time. R1, the gas 1, the rate of diffusion of gas 1, R2, rate of diffusion of gas 2, M2, molecular mass of gas 2, M1, molecular mass of gas 1. Then D2, density of gas 2, D1, density of gas 1, and T2, the time taken for gas 2 to diffuse, and T1 is the time taken for gas 1 to diffuse. Now let's solve a simple question.